At the close of the 19th century, physics stood at what many believed to be the edge of completion. The great pillars of classical science, Newton's laws of motion, Maxwell's equations of electromagnetism, and the laws of thermodynamics, appeared to describe the universe with extraordinary precision. From the motion of planets to the behavior of gases, everything seemed governed by clear, deterministic rules. Leading physicists of the time confidently claimed that the fundamental structure of nature had already been uncovered, and that future discoveries would involve little more than improving measurements and refining existing theories. This sense of intellectual satisfaction created an atmosphere in which young students were sometimes discouraged from entering physics, being told that there was nothing truly new left to discover. Yet beneath this surface of confidence, subtle cracks were forming. Certain experimental results stubbornly refused to fit within the elegant framework of classical physics. These were not minor discrepancies that could be ignored or smoothed out with better instruments. They were deep contradictions that hinted at something fundamentally incomplete in humanity's understanding of nature. One of the most troubling areas was the interaction between matter and radiation, especially the way objects emit light when heated. At first glance, this might have seemed like a narrow technical problem, but it would soon reveal itself as a profound challenge to the foundations of physics. Classical physics viewed energy as a continuous quantity. Just as water flows smoothly from a tap, energy was assumed to vary without interruption. This assumption worked remarkably well for everyday phenomena and even for many complex systems. Heat, light, sound, and electricity were all treated as waves or continuous processes described by differential equations that assumed smooth change over time and space. This continuity was deeply embedded in the mathematical language of physics and in the philosophical worldview of scientists. Nature, it was believed, did not make jumps. However, experiments involving heated objects told a different story. When an object is heated, it glows, emitting light of various colors depending on its temperature. Scientists carefully measured this radiation and plotted how much energy was emitted at each wavelength. These measurements produced precise curves that were consistent across different experiments and materials. The problem was that classical theories could not reproduce these curves correctly. Existing formulas worked only in limited ranges and failed catastrophically in others. The most dramatic failure came at high frequencies, corresponding to ultraviolet light. Classical physics predicted that as the wavelength became shorter, the emitted energy should increase without limit. According to theory, a hot object should release an infinite amount of energy in the ultraviolet range. This prediction was not only incorrect but physically absurd. Experiments showed that the energy peaked at a certain frequency and then dropped off sharply. This glaring contradiction became known as the ultraviolet catastrophe, a name that reflected both its mathematical severity and its philosophical implications. This crisis struck at the heart of classical physics. If the most trusted theories produced infinite energy where none existed, something was fundamentally wrong. Scientists attempted various fixes, introducing new assumptions or adjusting equations, but these efforts only partially succeeded. The deeper issue remained unresolved. The smooth, continuous picture of energy seemed incapable of describing reality at very small scales. It was within this intellectual tension that Max Planck carried out his work. Planck was not a rebel or a radical thinker seeking to overturn established ideas. On the contrary, he was deeply committed to classical physics and believed strongly in absolute laws of nature. He had great respect for tradition and mathematical consistency, and he was initially skeptical of speculative ideas. His goal was to find a solution to the radiation problem that preserved the continuity and determinism of classical theory. Planck approached the problem with extraordinary discipline. He immersed himself in experimental data, seeking a mathematical expression that would exactly match the observed radiation curves. Unlike some of his contemporaries, he did not rely on approximate fits or limited validity. He wanted a universal formula, one that worked perfectly for all frequencies and temperatures. This demand for precision reflected his belief that nature followed strict, exact laws that could be captured mathematically. As Planck worked, he encountered an uncomfortable truth. No matter how he adjusted classical assumptions, he could not derive a formula that matched the data across all ranges. The experimental curves were unforgiving. They demanded something new, something that classical physics could not provide. Faced with this impasse, Planck made a decision that would change the course of science, even though he did not fully understand or accept its implications at the time. In an act he later described as one of desperation, Planck introduced a radical assumption into his calculations. He proposed that energy could not be emitted or absorbed continuously, but only in discrete amounts. These amounts were proportional to the frequency of the radiation, meaning that higher frequency light involved larger packets of energy. This was a complete departure from classical thinking. Energy, long regarded as infinitely divisible, was suddenly treated as if it came in indivisible units. From a modern perspective, this step appears bold and visionary. But for Planck, it was deeply unsettling. He did not see it as a statement about physical reality, but rather as a mathematical trick to make the equations work. His primary concern was to reproduce the experimental results accurately. When he did so, the agreement was astonishing. The formula matched the data perfectly across all frequencies, resolving the ultraviolet catastrophe and providing a unified description of blackbody radiation. Despite this success, the crisis of classical physics was not immediately resolved in the minds of scientists. Many regarded Planck's assumption as a temporary measure, a convenient hypothesis that would eventually be replaced by a more classical explanation. Planck himself hoped for this outcome. He continued to believe that energy quantization was not a fundamental property of nature, but a reflection of incomplete understanding. Yet the crisis had already revealed something crucial: classical physics, for all its triumphs, was not the final word on reality. The failure to explain blackbody radiation exposed the limits of continuity, determinism, and classical intuition. It showed that even the most successful theories could break down under new experimental scrutiny. This realization marked a turning point in the history of science, forcing physicists to confront the possibility that nature behaved in ways that defied common sense. The crisis also highlighted the power of experimental evidence. No matter how elegant or philosophically appealing a theory might be, it must ultimately agree with observation. The radiation problem could not be dismissed or ignored because the data were precise, reproducible, and undeniable. This confrontation between theory and experiment set the stage for a profound transformation in scientific thinking. In retrospect, the crisis of classical physics was not a failure but a necessary step in the evolution of knowledge. It revealed the boundaries of existing ideas and opened the door to new concepts that would reshape humanity's understanding of the universe. The smooth, clockwork universe of classical mechanics gave way to a reality that was granular, probabilistic, and deeply strange. But this transition did not happen overnight. It began quietly, with a single problem, a stubborn set of experimental curves, and a physicist who was willing to follow the evidence even when it challenged everything he believed. This moment in history reminds us that scientific revolutions often emerge not from dramatic declarations, but from careful attention to anomalies. The crisis of classical physics was not announced with fanfare. It unfolded gradually through technical papers, laboratory measurements, and mathematical struggles, yet its impact was immense. By exposing the limitations of classical ideas, it prepared the ground for the quantum revolution that would soon follow, a revolution that began not with certainty, but with doubt, discomfort, and an honest confrontation with reality. As the 19th century drew to a close, the confidence of classical physics began to feel increasingly fragile, even if many scientists were reluctant to admit it openly. The foundations of physics were built on ideas that had worked flawlessly for generations, and abandoning them felt almost unthinkable. Determinism, continuity, and predictability were not just technical assumptions, they were deeply philosophical commitments about how nature itself must behave. To question them was to question the very identity of physics as a science. And yet, the evidence kept accumulating, quietly but persistently, that something essential was missing. The crisis was not confined to blackbody radiation alone. Other phenomena were also beginning to strain classical explanations. The behavior of electrons in atoms, the stability of matter, and the interaction between light and metal surfaces all hinted that classical laws were being pushed beyond their limits. But blackbody radiation was unique in its clarity and severity. It was not a marginal effect observed under exotic conditions. It was a universal phenomenon, measured with remarkable accuracy, and it contradicted theory in a way that could not be ignored or reinterpreted away. What made this situation especially unsettling was that the mathematics of classical physics was internally consistent. There were no obvious errors in the calculations that led to the ultraviolet catastrophe. The problem was not sloppy reasoning or experimental uncertainty, it was the assumptions themselves. Energy being continuous, matter interacting smoothly with radiation, and physical systems having infinitely many degrees of freedom were all reasonable ideas, until nature itself refused to cooperate. This realization created a deep tension within the scientific community. On one hand, there was a strong emotional and intellectual attachment to classical theory. On the other, there was an equally strong commitment to empirical truth. Physics had earned its authority precisely because it submitted its ideas to experimental verification. Now that verification was delivering an uncomfortable verdict. Something had to give. Max Planck found himself at the center of this tension, even though he did not seek that role. His personality and training made him an unlikely revolutionary. He valued order, precision, and timeless principles. He believed that the laws of nature were absolute, and that human understanding progressed by uncovering them more clearly, not by replacing them with fundamentally new frameworks. The idea that nature itself might operate according to rules that defied classical intuition was deeply troubling to him. Yet Planck was also intellectually honest. He could not ignore the experimental facts, nor could he pretend that existing theories explained them. This honesty forced him into a position that many of his contemporaries avoided, accepting a result that worked mathematically but made no intuitive sense within classical physics. In doing so, he unintentionally exposed the depth of the crisis. If even a conservative physicist like Planck had to abandon continuity to save agreement with experiment, then the problem was not superficial, it was structural. The crisis of classical physics thus became not merely a technical challenge, but a philosophical one. It raised fundamental questions about the nature of scientific explanation. Were physical theories meant to describe reality as it truly is, or were they merely tools for organizing observations? If a theory produced correct predictions using assumptions that seemed physically absurd, should those assumptions be taken seriously or dismissed as mathematical artifacts? These questions had no easy answers, and they forced physicists to reflect on the meaning of their own discipline. Another aspect of the crisis was generational. Older physicists, whose careers had been built on classical success, were often more resistant to radical change. Younger scientists, less invested in established frameworks, were more willing to explore unconventional ideas. This generational divide would soon play a crucial role in the development of quantum theory. But at the turn of the century, the tension was still unresolved. Classical physics was wounded, but not yet dethroned. It is important to understand that crises in science are not moments of chaos, but moments of intense creativity. When established ideas fail, they create space for new ways of thinking. The crisis of classical physics did exactly that. It forced scientists to confront the limits of their assumptions and to consider possibilities that would have seemed absurd only a few decades earlier. Discreteness, probability, and uncertainty began to enter the conversation, even if they were initially resisted. The blackbody problem, in particular, demonstrated that nature might impose fundamental limits on how energy is distributed and exchanged. This was a radical departure from the classical view, in which limits were imposed only by practical constraints, not by nature itself. The idea that there could be a smallest possible unit of energy challenged deeply held beliefs about divisibility and continuity. It suggested that at a microscopic level, the universe might be granular rather than smooth. As this realization slowly spread, it changed the way physicists approached other unsolved problems. Instead of assuming that classical concepts must apply at all scales, scientists began to ask whether new principles might govern the microscopic world. This shift in attitude was one of the most important consequences of the crisis. Even before quantum mechanics was fully formulated, the mindset of physics was changing. The crisis also revealed the power of mathematical abstraction. Planck's formula worked because it captured the empirical behavior of radiation, even if its underlying meaning was unclear. This showed that mathematical consistency and experimental agreement could sometimes outrun physical intuition. The equations seemed to know more about nature than the physicists who wrote them. This realization would later become a defining feature of modern theoretical physics. At the same time, the discomfort caused by this situation should not be underestimated. Many physicists felt that the unity and clarity of classical physics were being lost. The idea that nature might be fundamentally probabilistic or discontinuous seemed to undermine the goal of complete understanding. The crisis thus provoked not only excitement, but also anxiety about the future direction of science. In retrospect, the crisis of classical physics appears inevitable. Classical theories were developed to describe macroscopic phenomena, where quantum effects are negligible. Their success in that domain was extraordinary, but it created the illusion of universality. When experiments began probing smaller scales and higher energies, the limitations of those theories became unavoidable. The crisis was the natural result of extending old ideas beyond their proper domain. What makes this period so remarkable is how quietly revolutionary it was. There were no dramatic announcements declaring the end of classical physics. Instead, there were careful measurements, technical papers, and cautious proposals. The transformation unfolded gradually, driven by the steady pressure of experimental evidence. This slow pace made the revolution more profound, not less. It ensured that new ideas were not adopted lightly, but because they were unavoidable. By exposing the failure of classical assumptions, the crisis prepared the ground for a new understanding of nature. It showed that the universe is not obligated to conform to human expectations or philosophical preferences. Instead, science must adapt to reality, even when reality is strange, counterintuitive, or unsettling. This lesson, learned at the turn of the 20th century, remains central to scientific inquiry today. The crisis of classical physics was therefore not an end, but a beginning. It marked the moment when certainty gave way to questioning, when smooth continuity gave way to discreteness, and when absolute predictability began to dissolve. Out of this crisis emerged a new vision of the universe, one that would challenge common sense but offer unprecedented explanatory power. And at the heart of this transformation stood a simple, but devastating realization: the old rules were no longer enough. At the heart of the scientific storm that surrounded the turn of the 20th century stood a deceptively simple problem: how does a heated object emit light? This question, which seemed almost mundane compared to grand cosmic mysteries, became the battleground on which classical physics began to collapse. Max Planck's struggle with blackbody radiation was not a sudden breakthrough or a moment of inspiration, but a long, difficult intellectual journey marked by persistence, frustration, and an unwavering respect for experimental truth. A blackbody is an idealized physical system, one that absorbs all electromagnetic radiation that falls upon it and emits radiation solely as a function of its temperature. Physicists used blackbodies because they offered a clean, universal case, free from the messy details of specific materials. In laboratories, these were approximated using heated cavities with small holes, allowing radiation to escape and be measured with great precision. By the late 19th century, experimentalists had mapped the spectrum of blackbody radiation in extraordinary detail, producing curves that showed exactly how much energy was emitted at each frequency for a given temperature. These curves had several unmistakable features. As temperature increased, the total energy emitted increased. The peak of emission shifted toward higher frequencies, meaning hotter objects glowed with bluer light. And crucially, the energy did not increase indefinitely at high frequencies. Instead, it rose to a maximum and then dropped sharply. These results were consistent, reproducible, and undeniable. Nature was speaking clearly. The problem was that theory could not listen properly. Classical physics approached radiation using two main ideas. One treated radiation as waves governed by electromagnetism, while the other applied statistical mechanics to the motion of particles. Both approaches achieved partial success. Certain formulas worked well at low frequencies, accurately describing infrared radiation. Others worked at higher frequencies but failed elsewhere. No single classical theory could explain the entire spectrum. This piecemeal success masked a deeper failure. The assumptions underlying these theories were incompatible with the experimental data when applied universally. The most severe contradiction emerged when classical statistical mechanics was applied rigorously. According to the equipartition theorem, energy should be evenly distributed among all possible modes of vibration. When applied to electromagnetic radiation inside a cavity, this led to the conclusion that there were infinitely many modes at high frequencies, each contributing energy. The result was a prediction of infinite total energy, a conclusion that directly contradicted reality. This was not a minor error, it was a catastrophic failure. Max Planck entered this problem with a unique background. He was deeply trained in thermodynamics and held a philosophical belief in the absolute validity of the second law of thermodynamics. He believed entropy was a fundamental principle of nature, not merely a statistical convenience. This belief guided his approach to blackbody radiation. Rather than starting from electromagnetic theory alone, he tried to derive the radiation law from thermodynamic principles, hoping to anchor it in what he believed were unshakable foundations. Planck devoted years to this problem, carefully analyzing experimental data and testing mathematical forms that might fit the observed curves. His method was systematic rather than speculative. He sought a formula that would interpolate smoothly between the known limits, matching low-frequency and high-frequency behavior while remaining consistent with thermodynamics. This was not guesswork, it was disciplined mathematical craftsmanship. Eventually, Planck succeeded in finding a formula that fit the experimental data perfectly. Presented in December 1900, his radiation law reproduced the observed spectrum across all frequencies and temperatures. From an empirical standpoint, the problem was solved. But for Planck, the deeper question remained: what did this formula mean? To derive his law, Planck had made an extraordinary assumption. He treated the energy of oscillators in the cavity walls as if it could only take on discrete values, multiples of a basic unit proportional to frequency. This step allowed him to calculate entropy in a way that matched experimental observations. Without it, the mathematics simply would not work. Yet this assumption clashed violently with classical ideas. Planck did not initially believe that energy was truly quantized. To him, this was a formal trick, a mathematical device introduced to make the equations yield correct results. He hoped that a more classical derivation would eventually be found, one that preserved continuity while explaining the same formula. In this sense, his struggle was deeply internal. He had solved the problem experimentally and mathematically, but at the cost of violating his own philosophical convictions. This tension between success and discomfort defines Planck's struggle with blackbody radiation. He stood between two worlds: the secure, orderly universe of classical physics and a new, unsettling vision hinted at by his own work. Unlike later quantum pioneers, Planck did not celebrate this rupture. He endured it, his commitment to truth forced him to accept a result he did not fully understand or believe. The scientific community's reaction mirrored Planck's own ambivalence. While his formula was praised for its accuracy, the underlying assumption of energy quanta was often ignored or downplayed. Many physicists treated the formula as an empirical law without worrying about its implications. This selective acceptance delayed the recognition of how radical Planck's step truly was. Yet the struggle was not in vain. By confronting the blackbody problem honestly and rigorously, Planck exposed the inadequacy of classical assumptions. His work showed that no amount of refinement within existing frameworks could resolve the contradiction. Something fundamentally new was required. Even if Planck himself resisted that conclusion, his struggle made it unavoidable for others. What makes this episode so powerful is its human dimension. Planck was not driven by ambition to overthrow established science. He was driven by loyalty to it. His willingness to confront uncomfortable results rather than dismiss them exemplifies the highest ideals of scientific integrity. He allowed the evidence to guide him, even when it led into unknown territory. The struggle with blackbody radiation also highlights the importance of persistence in science. This was not a problem solved overnight. It required years of careful thought, repeated failure, and constant engagement with experimental data. Planck's eventual success was built on a foundation of patience and intellectual honesty, qualities that are often overshadowed by dramatic narratives of sudden discovery. In retrospect, Planck's struggle appears as the opening act of the quantum revolution. But at the time, it felt more like a reluctant compromise than a triumph. He solved a pressing problem, yet opened a door he was hesitant to walk through. That hesitation makes his contribution all the more profound. It reminds us that revolutionary ideas often emerge not from bold speculation, but from quiet dedication to understanding nature as it truly is, even when the answer defies expectation. As the implications of Planck's radiation law slowly unfolded, the deeper meaning of his struggle with blackbody radiation became increasingly clear. What had begun as a technical attempt to fit experimental data evolved into a profound challenge to the conceptual foundations of physics. Planck had not merely adjusted an equation, he had unknowingly introduced a new way of thinking about energy itself. The discomfort he felt was a signal that something truly fundamental was at stake. Planck's method of derivation revealed the heart of the difficulty. To calculate entropy, he had to count the number of possible ways energy could be distributed among microscopic oscillators. Classical physics assumed that energy could be divided endlessly, leading to an infinite number of possible arrangements. This made entropy calculations impossible. By restricting energy to discrete units, Planck could finally perform the calculation. In doing so, he linked the success of his theory not to electromagnetism alone, but to the statistical structure of matter and radiation. This step exposed a hidden weakness in classical statistical mechanics. The idea of equipartition, which worked well for many systems, failed dramatically when applied to radiation. Planck's struggle revealed that classical statistics implicitly assumed continuity where nature did not permit it. This insight, though not fully appreciated at the time, would later become central to quantum theory. It showed that the microscopic rules governing energy distribution were fundamentally different from classical expectations. Despite the power of his result, Planck remained cautious. He continued to search for a classical explanation and resisted interpretations that treated energy quanta as physically real. This hesitation reflected not weakness, but intellectual discipline. Planck understood the gravity of what he had done and refused to embrace conclusions that he felt were not yet fully justified. His struggle was not against the data, but against the temptation to abandon rigor for convenience. Meanwhile, experimental physics continued to advance. New measurements confirmed the accuracy of Planck's law under increasingly precise conditions. The empirical success of the formula made it impossible to ignore. Even those who were skeptical of quantization had to admit that Planck's approach worked where all others had failed. The struggle was no longer about whether the law was correct, but about how it should be understood. This period marked a subtle but important shift in scientific attitude. Physicists began to accept that mathematical formalisms might reveal truths about nature that defied classical intuition. The Blackbody problem demonstrated that physical meaning could not always be extracted directly from familiar concepts. Instead, new concepts might be required, even if they initially seemed abstract or counterintuitive. The struggle also highlighted the limits of analogy. Classical physics relied heavily on analogies between different systems, such as mechanical oscillators and electromagnetic waves. These analogies broke down in the Blackbody problem. Radiation did not behave like a simple collection of classical oscillators. Planck's work showed that analogical reasoning, while powerful, had its limits when applied beyond its proper domain. As younger physicists examined Planck's results, they began to push further. Einstein's work on the photoelectric effect would soon suggest that quantization was not merely a mathematical convenience, but a property of light itself. This development transformed Planck's reluctant assumption into a bold physical claim. Although Planck initially resisted this interpretation, it demonstrated how his struggle had planted seeds that others would cultivate. The emotional dimension of this struggle is often overlooked. Planck experienced genuine unease as he watched the implications of his work unfold. The orderly, continuous universe he believed in was being replaced by one marked by discontinuity and uncertainty. Accepting this change required not only intellectual flexibility, but personal resilience. Planck's willingness to remain engaged, rather than retreat into dogmatism, speaks to his character as a scientist. Over time, the Blackbody problem came to be seen as a turning point rather than an isolated puzzle. It demonstrated that nature imposed fundamental constraints on energy exchange, constraints that could not be removed by better measurements or more sophisticated mathematics within classical frameworks. This realization reshaped the goals of physics, shifting focus from perfecting existing theories to discovering new principles. Planck's struggle also underscores the nonlinear nature of scientific progress. Breakthroughs are rarely clean or comfortable. They often involve provisional assumptions, unresolved tensions, and partial understanding. The fact that Planck did not fully grasp the significance of his own discovery does not diminish its importance. On the contrary, it highlights how science advances through collective effort across generations. In the years that followed, Planck would come to accept the reality of quantization more fully. Even as quantum mechanics evolved in directions he found philosophically challenging. Yet his early struggle with blackbody radiation remained a defining moment, both for his career and for physics as a whole. It was the moment when the classical picture of the universe was forced to confront its own limitations. Ultimately, the significance of Planck's struggle lies not only in the solution he provided, but in the example he set. He showed that true scientific progress requires humility before nature. When evidence contradicts expectation, the task of the scientist is not to defend belief, but to revise it. Through patience, honesty, and perseverance, Planck transformed a stubborn technical problem into the gateway of a new scientific era, even if he himself stepped through that gateway with hesitation rather than enthusiasm. At the dawn of the 20th century, the idea that energy might come in discrete packets was not just surprising, it was almost unthinkable. For centuries, natural philosophy and later physics had been built on the assumption of continuity. Motion was continuous, time flowed smoothly, and energy could be divided endlessly into smaller and smaller amounts. This belief was not merely a habit of thought, it was deeply embedded in the mathematics, experiments, and philosophical outlook of science. The birth of the quantum idea shattered this assumption at its core, and Max Planck stood at the precise point where this fracture occurred. When Planck introduced the notion that energy could only be exchanged in fixed amounts, he did not initially view it as a statement about the physical structure of reality. For him, It was a mathematical necessity forced upon him by the stubborn refusal of experimental data to conform to classical expectations. Yet whether he liked it or not, the implication was profound. If energy was quantized, then nature itself operated in jumps rather than flows. This single shift altered the conceptual landscape of physics forever. The essence of the quantum idea lay in a simple but radical proposal. The energy of an oscillator could only take on values that were integer multiples of a fundamental unit. This unit was proportional to the frequency of radiation and involved a new constant of nature, later called Planck's constant. The appearance of this constant was itself revolutionary. Classical physics had no place for such a number. It introduced a natural scale that separated the macroscopic world, where classical laws worked well, from the microscopic world, where they did not. What made this idea so disruptive was that it contradicted everyday intuition. In daily life, energy appears smooth and continuous. You can gently increase the brightness of a lamp or slowly raise the temperature of water. Nothing in ordinary experience suggests that energy is delivered in indivisible chunks. This disconnect between intuition and theory made the quantum idea deeply unsettling, even to those who recognized its mathematical power. Planck himself struggled with this implication. He believed strongly in the existence of absolute laws of nature, but he also believed that these laws should be understandable within a classical framework. The quantum hypothesis seemed to undermine that belief. It introduced an element of discreteness that appeared arbitrary and artificial. For years after his discovery, Planck hoped that quantization was not fundamental, but merely a feature of his method of calculation. Despite Planck's hesitation, the idea could not be contained. Once introduced, it began to reveal explanatory power far beyond blackbody radiation. The quantum concept provided a new lens through which previously mysterious phenomena could be understood. It suggested that the failure of classical physics was not accidental, but a sign that its underlying assumptions were incomplete. The true power of the quantum idea became evident when Albert Einstein took it seriously as a physical principle. In explaining the photoelectric effect, Einstein proposed that light itself behaved as if it consisted of individual quanta of energy. This was a dramatic step beyond Planck's original formulation. Planck had quantized the exchange of energy between matter and radiation. Einstein quantized the radiation itself. This move transformed the quantum hypothesis from a mathematical convenience into a claim about the nature of light. The implications were staggering. Light, long understood as a wave, now exhibited particle-like behavior. This wave-particle duality challenged the very categories through which physicists understood the world. Objects were no longer simply particles or waves. They could exhibit properties of both, depending on how they were observed. This idea would later be extended to matter itself, further blurring the boundary between classical concepts. The birth of the quantum idea also forced physicists to reconsider the meaning of explanation. In classical physics, explanation involved tracing effects back to causes through deterministic laws. Given complete information about a system, its future behavior could, in principle, be predicted exactly. Quantization disrupted this picture. It suggested that at a fundamental level, certain processes were governed not by smooth causality, but by discrete transitions. This shift had profound philosophical consequences. It raised questions about determinism, predictability, and the limits of human knowledge. If energy changes occurred in jumps, what determined when those jumps happened? Were they governed by hidden variables, or was nature inherently probabilistic? These questions would haunt physics for decades and remain subjects of debate even today. Another revolutionary aspect of the quantum idea was its universality. Planck's constant appeared to be the same everywhere, a fundamental feature of the universe rather than a property of specific systems. This universality suggested that quantization was not an isolated oddity, but a deep principle woven into the fabric of reality. The smallness of Planck's constant explained why quantum effects were invisible in everyday life, yet dominant at atomic scales. The birth of the quantum idea also changed the relationship between theory and experiment. Classical physics had often progressed by building theories grounded in intuitive models and then testing them experimentally. In the quantum case, the process was reversed. Experimental anomalies forced the introduction of abstract theoretical concepts that defied intuition. Physicists had to accept that mathematical consistency and empirical accuracy might take precedence over visualizable models. This new approach demanded a different kind of scientific imagination. Instead of picturing tiny billiard balls or continuous waves, physicists had to work with probabilities, operators, and abstract spaces. The quantum idea thus marked a departure not only from classical laws, but from classical ways of thinking. It required a willingness to let go of familiar mental images and trust in the language of mathematics. Planck's role in this transformation was unique. He did not embrace the quantum idea with enthusiasm, yet he defended its validity once it proved successful. His cautious acceptance lent credibility to the new concept. It signaled that quantization was not a speculative fantasy, but a serious response to empirical necessity. This balance between skepticism and openness was crucial in the early acceptance of quantum ideas. The birth of the quantum idea also illustrates how scientific revolutions often begin quietly. There was no immediate declaration that classical physics was obsolete. Instead, there was a gradual accumulation of evidence, reinterpretation, and conceptual adjustment. Planck's hypothesis entered the literature as a technical assumption, not a philosophical manifesto. Its revolutionary nature became apparent only in hindsight. As the quantum idea spread, it began to reshape entire fields of physics. Atomic theory, spectroscopy, and solid-state physics all found new coherence under the quantum framework. Phenomena that had seemed unrelated were suddenly connected through a common principle. This unifying power further confirmed that quantization was not an isolated trick, but a foundational insight. The emotional impact of this shift on physicists should not be underestimated. Many experienced a sense of loss as the clarity and determinism of classical physics gave way to uncertainty and abstraction. Others felt exhilaration at the opening of new intellectual territory. The birth of the quantum idea thus marked a moment of both crisis and creativity, uncertainty and opportunity. In the end, the quantum idea did not merely add a new chapter to physics, it rewrote the entire book. It challenged assumptions that had gone unquestioned for centuries and forced a reevaluation of what it means to understand nature. That this transformation began with a reluctant hypothesis introduced by a conservative physicist is one of the great ironies of scientific history. Planck may not have intended to unlock a new universe, but by introducing the idea of energy quanta, he did exactly that. The birth of the quantum idea marked the moment when physics crossed a threshold, leaving behind the comforting continuity of classical thought, and stepping into a world where nature speaks in discrete whispers rather than smooth flows. This moment would define the trajectory of modern science, shaping our understanding of reality in ways that continue to unfold today. As the quantum idea began to circulate within the scientific community, its true depth slowly revealed itself, not through sudden acceptance, but through sustained tension and debate. The proposal that energy was exchanged in discrete packets did more than solve a specific problem. It quietly dismantled the classical image of nature piece by piece. What made this transition so difficult was that quantization did not merely modify existing laws, it redefined the very language through which physical reality was described. One of the earliest signs of this deeper shift was the growing realization that classical continuity was not just empirically inadequate, but conceptually misleading at microscopic scales. The assumption that physical quantities could vary smoothly without limit had been so successful in macroscopic physics that it was treated almost as a metaphysical truth. The quantum idea challenged this belief directly. It suggested that continuity was not a universal principle, but an approximation that emerged only when many quantum events were averaged together. This realization forced physicists to confront a disturbing possibility. the fundamental structure of reality might be inaccessible to direct intuition. If energy, and later matter itself, behaved in discrete jumps, then the smooth world perceived by human senses was not fundamental, but emergent. This idea undermined the classical hope that nature could be fully understood through mechanical analogies and visual models. The quantum world resisted being pictured in familiar terms. As the implications of quantization spread, the idea began to reshape scientific methodology. Physicists became increasingly willing to accept abstract principles if they led to accurate predictions, even when those principles defied visualization. This marked a profound shift in the philosophy of science. Mathematical structure, rather than physical imagery, became the primary guide to understanding. Equations were no longer just descriptions of known mechanisms, they became windows into unseen layers of reality. The quantum idea also altered the meaning of causality. In classical physics, causes and effects were linked through continuous chains of interaction. Given complete knowledge of a system at one moment, its future could be predicted with certainty. Quantization disrupted this vision. Energy transitions occurred in sudden jumps, without any classical description of how the system moved between states. The absence of a continuous process raised questions about what it even meant for one event to cause another at the quantum level. These questions became more pressing as the quantum hypothesis was applied to atomic structure. Atoms, once imagined as miniature solar systems governed by classical motion, began to appear as systems governed by discrete energy levels. Electrons did not spiral smoothly toward the nucleus as classical theory predicted they should. Instead, they occupied stable states and jumped abruptly between them, emitting or absorbing energy quanta in the process. The stability of matter itself, once a mystery, now found an explanation rooted in quantization. This new picture of the atom reinforced the idea that the quantum hypothesis was not an isolated fix, but a universal principle. The same constant that appeared in blackbody radiation governed atomic spectra and chemical behavior. This unity strengthened confidence in the quantum framework, even as it deepened conceptual unease. The universe appeared coherent, but in a way that no longer aligned with classical common sense. The birth of the quantum idea also redefined the role of measurement in physics. Classical measurement was assumed to reveal pre-existing properties of a system without disturbing it significantly. Quantum theory challenged this assumption. Measuring a quantum system often involved exchanging energy quanta with it, fundamentally altering its state. This meant that observation was no longer passive, it became an active participant in physical processes. This shift had profound philosophical consequences. It blurred the boundary between observer and observed, raising questions about objectivity and the limits of knowledge. If the act of measurement influenced the outcome, could physics still claim to describe reality as it exists independently of observation? These questions did not arise immediately from Planck's work, but they were implicit in the quantum idea from the beginning. As debates intensified, the quantum concept attracted both fierce criticism and passionate defense. Some physicists argued that quantization was a temporary placeholder, a sign of incomplete theory rather than a fundamental truth. Others embraced it as evidence that nature operated according to principles radically different from classical expectations. This division reflected deeper philosophical differences about what science should aim to achieve: intuitive understanding or predictive accuracy. Over time, the predictive success of quantum ideas became impossible to ignore. Spectroscopy, which studies the interaction of light with matter, found a natural explanation in terms of discrete energy levels. Chemical bonding, once described only empirically, began to make sense through quantum principles. Even the behavior of solids, including electrical conductivity and magnetism, could be traced back to quantized interactions at the atomic level. The cumulative weight of these successes transformed the quantum idea from a controversial hypothesis into a foundational principle. Yet this transformation did not eliminate discomfort. Instead, it shifted the source of unease from empirical adequacy to to conceptual interpretation. Physicists could calculate results with extraordinary precision, but explaining what those calculations meant in physical terms proved far more challenging. This tension gave rise to multiple interpretations of quantum theory, each attempting to reconcile quantization with broader philosophical commitments. Some emphasized probability and indeterminacy, others sought hidden variables that might restore determinism. The diversity of interpretations reflected the depth of the conceptual rupture introduced by the quantum idea. No single narrative could fully capture its implications. Planck himself watched these developments with a mixture of pride and reservation. He accepted the reality of quantization as evidence accumulated, but he remained uneasy with the abandonment of classical ideals. His journey mirrored that of physics itself, a gradual transition from certainty to acceptance of fundamental limits. In this sense, the quantum idea was not just a scientific innovation, but a lesson in intellectual humility. The birth of the quantum idea also reshaped humanity's broader worldview. It challenged the belief that the universe was fully predictable and mechanically transparent. Instead, it suggested a reality structured by probabilities, thresholds, and discrete events. This vision resonated beyond physics, influencing philosophy, literature, and even art, as thinkers grappled with the implications of a universe that resisted complete control and understanding. Despite its abstract nature, the quantum idea eventually proved to be intensely practical. Technologies based on quantum principles transformed everyday life, even as their underlying concepts remained counterintuitive. This paradox highlighted one of the most striking features of the quantum revolution: the ability of humans to harness phenomena they do not fully comprehend intuitively. In hindsight, the birth of the quantum idea appears as a necessary evolution rather than a rupture. Classical physics did not fail, it found its proper domain. The quantum framework did not replace classical laws, but revealed the deeper structure from which they emerge. Continuity, determinism, and predictability survive as approximations, valid when quantum effects average out. The enduring significance of the quantum idea lies in its demonstration that nature's deepest truths may be hidden beneath layers of approximation and habit. Discovering those truths requires not only technical skill, but the courage to question assumptions that feel self-evident. The reluctance with which the quantum idea was born is a testament to its revolutionary power. From a single assumption introduced to solve a stubborn problem, a new universe unfolded. The quantum idea reshaped physics, altered philosophy, and redefined humanity's relationship with nature. It taught scientists that understanding does not always mean visualizing, that certainty is not always attainable, and that the universe may operate according to rules that challenge even the most disciplined imagination. In that sense, the birth of the quantum idea was not just a moment in scientific history, but a turning point in the human quest to understand reality itself. When Max Planck introduced his new constant into physics, he could not have known that he was defining a boundary between two worlds. Planck's constant was not just another number to be added to the growing list of physical constants, it was a signal that nature itself had a smallest scale of action. This constant, denoted by the symbol h, represented the proportionality between the energy of a quantum and the frequency of radiation. On the surface, it appeared as a technical factor in an equation, but its meaning reached far beyond mathematics. Planck's constant revealed that energy exchanges at the microscopic level are governed by a fundamental unit. No matter how refined an experiment might become, energy could not be transferred in amounts smaller than this basic quantum. This idea introduced a limit to divisibility that classical physics had never considered. In the classical view, there was no smallest unit of energy, just as there was no smallest length or time. Planck's constant quietly overturned that assumption, suggesting that nature itself imposes boundaries on how finely physical processes can be divided. One of the most striking features of Planck's constant is its smallness. Its numerical value is so tiny that its effects are completely negligible in everyday life. This explains why classical physics works so well at human scales. The smooth flow of energy, the continuous motion of objects, and the apparent determinism of the macroscopic world all emerge because Planck's constant is small compared to the energies and actions involved in daily experience. Yet at the atomic and subatomic level, this same constant becomes dominant, reshaping the rules entirely. The introduction of Planck's constant forced physicists to rethink the concept of measurement. In classical physics, measuring a system could, in principle, be done with arbitrary precision. Any disturbance caused by measurement could be made smaller by using gentler techniques. Planck's constant showed that this ideal was unattainable at the quantum level. There is a fundamental limit to how precisely certain quantities can be known simultaneously, a limit rooted directly in the value of this constant. This realization laid the groundwork for later developments in quantum mechanics, including the uncertainty principle. While Planck himself did not formulate this principle, his constant made it unavoidable. The existence of a smallest unit of action meant that attempts to measure position, momentum, energy, or time with infinite precision would inevitably fail. Nature itself resisted such exactness, not because of experimental imperfections, but because of its own structure. Planck's constant also provided a new way to understand the transition between classical and quantum behavior. When the actions involved in a system are large compared to Planck's constant, quantum effects average out, and classical laws emerge as excellent approximations. When actions are comparable to this constant, quantum behavior dominates. This insight revealed that classical physics was not wrong, but incomplete. It was a limiting case of a deeper theory, valid only under certain conditions. The universality of Planck's constant added to its significance. Unlike material properties that vary from one substance to another, this constant appeared everywhere in quantum phenomena. Whether describing radiation, atoms, electrons, or chemical bonds, the same value governed the behavior of all systems. This universality suggested that Planck's constant was woven into the fabric of the universe, a fundamental feature rather than a convenient parameter. Beyond physics, Planck's constant had philosophical implications. It challenged the notion that nature could be known with unlimited precision, and that reality could be fully captured by deterministic laws. The constant implied that there were limits to knowledge built into the structure of the universe. This did not mean that science was powerless, but that its power had boundaries defined by nature itself. Despite its profound implications, Planck himself was slow to embrace the full meaning of his constant. He initially viewed it as a formal element of his radiation law rather than a key to a new worldview. Over time, as quantum theory developed and experimental evidence accumulated, the central role of Planck's constant became undeniable. It emerged as the cornerstone of quantum physics, the scale against which all microscopic phenomena are measured. Today, Planck's constant stands as a symbol of the quantum revolution. It marks the point where classical intuition gives way to a deeper, more subtle understanding of reality. Through this single number, Max Planck revealed that the universe is not infinitely divisible, not endlessly smooth, but structured in discrete steps. In doing so, he gave science a new lens through which to view nature, one that continues to shape our understanding of the world at its most fundamental level. When Max Planck presented his radiation law and the idea of energy quanta to the scientific world, the reaction was far from immediate acceptance. The concept struck at the heart of classical physics, and with that came resistance, hesitation, and deep intellectual doubt. What makes this period especially compelling is that even Planck himself was among the skeptics. The man who opened the door to the quantum universe was not eager to walk through it, and this reluctance reveals much about both his character and the nature of scientific revolutions. Planck had built his career on the belief that the laws of nature were absolute, continuous, and discoverable through classical reasoning. He held deep respect for the achievements of Newtonian mechanics and Maxwell's electromagnetism, viewing them as near, perfect expressions of natural order. To accept that energy itself was quantized felt to him like accepting a flaw in this grand structure. For years after his discovery, he hoped that the quantum assumption would eventually be replaced by a more traditional explanation that preserved continuity. This personal skepticism was mirrored by the wider scientific community. Many physicists treated Planck's quantum hypothesis as a purely mathematical device, useful for calculations, but not to be taken literally. They admired the accuracy of his formula, but avoided confronting its implications. In lectures and textbooks, Planck's law was often presented without emphasizing the radical nature of energy quantization. This selective acceptance allowed classical physics to maintain its authority, at least on the surface. The resistance was not based on ignorance or stubbornness, but on deeply rooted habits of thought. Classical physics had succeeded so spectacularly that abandoning its assumptions felt unnecessary and even irresponsible. Continuity and determinism were not just technical features, they were philosophical commitments about how nature should behave. The quantum idea appeared to violate these commitments without offering an intuitive alternative. Planck himself struggled emotionally with the consequences of his work. He described the introduction of energy quanta as an act of desperation rather than inspiration. Unlike later physicists, who embraced the strange implications of quantum theory, Planck approached them with caution. He accepted the necessity of the hypothesis, but resisted interpreting it as a statement about physical reality. This internal conflict lasted for many years and shaped his cautious attitude toward the emerging quantum theory. As experimental evidence accumulated, however, doubt became increasingly difficult to maintain. Phenomena such as the photoelectric effect, atomic spectra, and specific heat anomalies all pointed toward quantization as a real feature of nature. Each new confirmation chipped away at resistance, forcing physicists to confront the possibility that the classical worldview was incomplete. The weight of evidence gradually shifted the debate from whether quantization was real to how it should be understood. This period of resistance and doubt highlights an important truth about scientific progress. Revolutionary ideas are rarely embraced immediately, especially when they challenge foundational assumptions. Even compelling evidence does not erase hesitation overnight. Acceptance often requires a generational shift as younger scientists, less attached to established frameworks, explore new ideas with greater freedom. Planck's own evolution reflects this process. Over time, he came to accept the physical reality of quanta, even if he remained uneasy about some of their implications. He defended quantum theory against critics and recognized its explanatory power, acknowledging that nature was revealing itself in unexpected ways. This gradual acceptance did not mean abandoning classical physics entirely, but recognizing its limits. The resistance to quantum ideas also served a constructive role. Skepticism forced proponents to strengthen their arguments, refine experiments, and clarify interpretations. Without doubt, the quantum theory might have developed more quickly, but perhaps less rigorously. The tension between old and new ideas ensured that the emerging framework was tested thoroughly before gaining widespread acceptance. This phase of doubt also reminds us that scientific revolutions are not purely intellectual events. They involve human emotions, identities, and commitments. For Planck, accepting quantization meant questioning beliefs he had held for decades. For the broader community, it meant rethinking the nature of explanation and understanding. These challenges made resistance not only understandable, but inevitable. In the end, the persistence of quantum effects overcame skepticism. The success of quantum theory in explaining and predicting phenomena forced a re-evaluation of long-held assumptions. Resistance gave way not to blind acceptance, but to a cautious recognition that the universe was more complex than classical physics had imagined. Planck's journey through doubt and resistance stands as a powerful example of scientific integrity. He did not cling blindly to tradition, nor did he rush to embrace novelty for its own sake. Instead, he allowed evidence to guide him, even when it led away from comfort and certainty. This balance between skepticism and openness is one of the greatest strengths of science. The story of resistance to Planck's ideas teaches us that progress often begins with discomfort. New truths rarely fit neatly into existing frameworks. They challenge identities, question assumptions, and demand intellectual courage. By enduring doubt rather than denying it, Planck and his contemporaries laid the groundwork for a deeper understanding of nature, one that continues to shape modern science and human thought. Once Max Planck introduced the quantum idea, its influence began to spread far beyond the problem it was meant to solve. What started as a cautious mathematical assumption soon became the spark that ignited one of the greatest transformations in the history of science. Planck himself did not drive this transformation forward with bold claims, but his work created the foundation upon which others could build. The true power of his idea was revealed as it inspired a new generation of physicists to rethink the structure of reality. Among the first to recognize the deeper significance of Planck's work was Albert Einstein. In 1905, Einstein applied the concept of energy quanta to explain the photoelectric effect, a phenomenon in which light striking a metal surface causes electrons to be ejected. Classical wave theory could not account for the observed behavior, but Einstein's proposal that light consisted of discrete energy packets provided a clear explanation. This step extended Planck's idea from the interaction between matter and radiation to the nature of light itself, marking a crucial turning point. The influence of Planck's quantum concept continued with Niels Bohr, who used it to construct a new model of the atom. Bohr proposed that electrons could occupy only certain allowed energy levels, and that transitions between these levels involved the emission or absorption of quanta. This model explained atomic spectra with remarkable accuracy, revealing a hidden order within the atom that classical physics had failed to uncover. The atom was no longer a miniature solar system, but a quantum structure governed by discrete rules. As these ideas developed, it became clear that Planck's constant was a unifying element across seemingly unrelated phenomena. Spectroscopy, atomic stability, and radiation all followed the same quantum principles. This unity suggested that Planck's insight was not a narrow solution, but a doorway to a deeper understanding of nature. Each successful application strengthened confidence in the quantum framework and encouraged further exploration. The inspiration drawn from Planck's work culminated in the development of quantum mechanics during the 1920s. Physicists such as Werner Heisenberg, Erwin Schrödinger, and Paul Dirac built comprehensive mathematical frameworks that described quantum behavior with unprecedented precision. While their approaches differed, they all relied on the fundamental notion of quantization introduced by Planck. Without that initial step, the formal structure of quantum mechanics would have been impossible. This transformation also reshaped scientific collaboration and competition. The quantum revolution brought together physicists from different countries and traditions, united by a shared challenge. Conferences and debates became arenas where new ideas were tested and refined. Planck's early work served as a common reference point, a reminder that even the most established assumptions could be overturned by careful attention to evidence. Beyond theoretical physics, the inspiration of Planck's idea extended into technology. As quantum principles were better understood, they were harnessed to create new tools and devices. Lasers, transistors, and modern electronics all rely on quantum behavior. These practical outcomes demonstrated that abstract ideas about energy quanta had tangible consequences, transforming everyday life in ways Planck could never have imagined. Planck's influence also reached into philosophy and culture. The quantum view of nature challenged classical notions of certainty, causality, and objectivity. Philosophers grappled with the implications of a universe governed by probabilities and discrete events. Artists and writers drew inspiration from the idea that reality was layered and mysterious, reflecting the cultural impact of the quantum revolution. What makes Planck's role in this transformation particularly striking is his humility. He did not claim ownership of the quantum revolution, nor did he seek to impose his interpretation on others. Instead, he allowed his idea to evolve through the work of others, accepting that scientific progress is a collective endeavor. His openness to new developments, even when they challenged his own preferences, exemplified intellectual maturity. As the quantum framework matured, it became clear that Planck's initial insight had altered the trajectory of science permanently. Classical physics remained valid within its domain, but it was now understood as part of a larger picture. The universe revealed itself as more complex and subtle than previously imagined, governed by principles that required new forms of reasoning. The inspiration sparked by Planck's work continues to this day. Research in quantum computing, quantum communication, and fundamental physics builds directly on the ideas he introduced. Each new discovery traces its lineage back to that moment when energy was first treated as quantized. The ripple effect of Planck's insight has extended across more than a century, shaping both knowledge and technology. In reflecting on this legacy, one sees that Planck's greatest contribution was not a single equation or constant, but a change in perspective. He showed that progress sometimes requires accepting results that conflict with intuition and tradition. By opening the door to the quantum world, Planck inspired generations of scientists to explore the unknown with rigor and humility. His idea transformed physics from a nearly complete system into an open frontier, reminding humanity that the universe always has more to reveal. Max Planck's legacy reaches far beyond the moment he introduced the quantum idea. It extends into nearly every aspect of modern science, technology, and human understanding. What began as a reluctant hypothesis to solve a specific problem evolved into a foundation upon which the modern world is built. Planck did not simply contribute to physics, he changed the direction of scientific thought, leaving an imprint that continues to shape how humanity explores and interprets reality. One of the most enduring aspects of Planck's legacy is the way his work redefined the limits of human knowledge. By introducing a fundamental constant that sets a smallest scale of action, he revealed that nature itself imposes boundaries on precision and certainty. This insight transformed science from a quest for absolute determinism into a disciplined exploration of probabilities and constraints. The universe, once imagined as a perfectly predictable machine, emerged as a system governed by both order and limitation. Planck's influence is also deeply embedded in modern technology. Devices that define contemporary life rely on principles rooted in his work. Semiconductors, which form the basis of computers and smartphones, operate according to quantum rules governing electron behavior in solids. Lasers, used in medicine, communication, and industry, depend on controlled quantum transitions between energy levels. Even medical imaging technologies and precise timekeeping systems trace their origins to quantum mechanics made possible by Planck's constant. Beyond practical applications, Planck's legacy lies in the transformation of scientific culture. His work demonstrated that even the most established theories must remain open to revision. This attitude has become a defining feature of modern science. Researchers today approach nature with a balance of confidence and humility, recognizing that success in one domain does not guarantee universal validity. Planck's example encourages scientists to follow evidence wherever it leads, even when it challenges deeply held beliefs. Planck's personal life adds a human dimension to his legacy. He lived through periods of profound personal tragedy and historical turmoil, yet maintained his commitment to truth and reason. His resilience in the face of loss and uncertainty mirrored the intellectual resilience he showed in his scientific work. This combination of personal integrity and scientific rigor has made him a model of ethical responsibility in science. The philosophical impact of Planck's work has been equally profound. The quantum worldview reshaped debates about realism, determinism, and the nature of causality. It challenged the idea that science could provide a complete, intuitive picture of reality, suggesting instead that some aspects of nature may remain fundamentally abstract. These questions continue to influence philosophy, shaping discussions about knowledge, observation, and the limits of explanation. Education and research institutions also bear Planck's imprint. His name is associated with centers of excellence dedicated to advancing scientific knowledge. These institutions embody the spirit of inquiry he exemplified, fostering interdisciplinary collaboration and pushing the boundaries of understanding. They serve as living reminders that scientific progress depends on both individual insight and collective effort. Planck's legacy also highlights the interconnectedness of scientific discovery. His work did not exist in isolation. It inspired and was expanded by others. The quantum revolution was a collaborative achievement, yet it required Planck's initial step to begin. This interconnected legacy underscores the cumulative nature of knowledge, where each contribution builds upon those that came before. In a broader cultural sense, Planck's ideas influenced how society views uncertainty and complexity. The acceptance of limits and probabilities in physics has parallels in other fields, from economics to psychology. The quantum perspective encourages a more nuanced understanding of systems, acknowledging that complete control and prediction may be impossible, yet meaningful insight remains attainable. As science continues to advance, Planck's legacy remains relevant. New fields such as quantum information science and fundamental cosmology build directly on the principles he introduced. Researchers continue to explore the implications of quantization at ever smaller scales, testing the boundaries of current theories. Each step forward echoes Planck's willingness to confront the unknown with discipline and honesty. Ultimately, Max Planck's lasting impact lies in the lesson his life and work convey. He showed that true progress often begins with doubt, that humility before nature is a strength rather than a weakness, and that the pursuit of truth requires patience and courage. By unlocking the quantum universe, Planck did more than transform physics. He reshaped humanity's approach to understanding the world, leaving a legacy that endures in both knowledge and spirit.